They thought it was just passing by. For months, astronomers watched 3I Atlas drift silently through the stars, a cold interstellar wanderer with no intention and no destination. But everything changed after perihelion, because in November 2025, new data emerged, and it changed everything. Instead of slipping back into the dark, it adjusted course, not randomly, deliberately. Its new trajectory bypasses the inner solar system entirely and heads straight toward the most dangerous gravity well we know, Jupiter, and not just Jupiter itself, but a point near its magnetic equator, where captured material can spiral toward the moons, Europa, Ganymede, Callisto. Now, scientists are racing against time to understand what this object truly is, because if this isn't just another comet, and its destination isn't random, then what's coming on March 16th, 2026 might not be a coincidence at all. Tonight, we follow the updated flight path of 3I Atlas and ask the question that even the most skeptical researchers are starting to whisper. What is it trying to reach? And why does that destination terrify the people tracking it? For months, 3I Atlas behaved like any other interstellar visitor, quiet, detached, and mathematically predictable. After its discovery in July 2025, astronomers around the world tracked its trajectory using models refined over decades. Its orbit was labelled hyperbolic, meaning it wasn't gravitationally bound to the Sun. Like Oumuamua and Borisov before it, this object was expected to enter our system, curve around the Sun, and exit, untouched, unnoticed, and unchanged. But that prediction didn't hold, because after perihelion, when 3I Atlas made its closest approach to the Sun, something unexpected began to happen. Deep space tracking data, initially thought to contain minor anomalies, revealed a pattern that could not be explained by solar gravity alone. Instead of exiting the solar system along its expected path, 3I Atlas began to deviate, slightly at first, then measurably. Its vector had changed. The object wasn't drifting anymore, it was steering. This deviation wasn't dramatic like a slingshot maneuver. It was subtle, so subtle that it took several days of continuous observation from facilities like JPL, the Minor Planet Center, and European observatories to confirm. But once confirmed, the implications were significant. It meant that something had imparted thrust to the object, and if that was true, then the path it was now following wasn't just a result of celestial mechanics, it was potentially a decision. The new vector, calculated using updated ephemeris data, placed 3I Atlas on a long, shallow outbound curve, one that appeared to head directly toward the Jovian system. According to projections, it would pass within approximately 54 million kilometers of Jupiter on March 16, 2026. That's well within Jupiter's Hill sphere, the region in which the planet's gravity dominates over that of the Sun. In short, it was now on a path that could bring it into Jupiter's control. That alone was shocking. But it wasn't just the destination that caught astronomers off guard, it was the timing. The course correction seemed to occur within 2 weeks after perihelion, a period during which the object had remained visually inert. No visible jets, no coma, no signs of outgassing. And yet, its velocity had changed. Observations recorded a shift of roughly 60 meters per second. That's not something you expect from an object that shows no signs of venting material. It's equivalent to a sustained acceleration, like a spacecraft making a mid-course correction. To many observers, this created a deep contradiction. The object looked dead. It flew like it was alive. Scientists were quick to offer natural explanations. Some proposed micro-outgassing, tiny jets of sublimated gas escaping through minuscule surface fractures that wouldn't produce a visible coma. Others argued it was a measurement error, perhaps atmospheric distortion or misalignment between datasets. But the longer 3I Atlas was tracked, the more consistent the deviation became. It wasn't noise, it was signal. And as the models were recalculated, a picture began to emerge. This wasn't just a wayward rock drifting through space. This was something that had changed course, not randomly, not erratically, but with intention, either natural or not. If the course change was natural, it defied conventional cometary physics. The lack of visible outgassing, the absence of a coma, and the perfectly planar thrust profile, with no out-of-plane vector or A3 or 0, all suggest a type of behaviour no known comet has ever shown. If it was artificial, if the thrust was the result of some form of active propulsion, then 3I Atlas would be the first object in recorded history to exhibit such control. Regardless of the mechanism, the result is the same. 3I Atlas is now heading straight toward the most complex and dangerous gravitational structure in our solar system. The question is no longer where it's going. It's why. In orbital mechanics, perfection doesn't exist. Natural bodies in space wobble, tumble, and deviate. Their paths are shaped by gravity, but always softened by chaos. Slight outgassing here, a minor torque there, micrometeorite impacts, rotational irregularities. Over time, even the most stable orbits develop statistical drift. When scientists track comets and asteroids, they factor in these imperfections, expecting the messy fingerprints of nature. But 3I Atlas isn't following that script. After its unexpected post-perihelion acceleration, researchers began to analyze not just the object's change in speed, but the geometry of that change. Using precise astrometric data collected from ground-based telescopes, spaceborne assets, and radar echoes, a detailed breakdown of the object's thrust components was calculated. These thrust vectors, labelled A1, A2, and A3, are standard tools in modelling non-gravitational accelerations. A1 describes radial thrust, toward or away from the Sun. A2 describes tangential thrust, along the direction of motion, and A3 describes out-of-plane thrust, perpendicular to the orbital plane. In real-world comets, these three values fluctuate, often wildly. Jets erupt from irregular surfaces, rotation adds torque, and even under ideal symmetry, no comet confines its motion perfectly to 2 dimensions. Yet in the case of 3I Atlas, something extraordinary happened. A3 was measured as exactly 0. Not approximately 0, not statistically small. 0 within the margin of error across multiple independent observatories and tracking models. To anyone familiar with comet physics, that's a red flag. A 0 out-of-plane thrust means that the object was accelerating, but doing so only within its orbital plane. That's not messy, that's not chaotic, that's precise. And precision of that kind, sustained over 20-plus days, is virtually impossible without control. Natural outgassing doesn't behave like that. Even if jets are firing from symmetrical positions on a rotating nucleus, minor imperfections in ice density, vent placement, spin wobble, or thermal conductivity should eventually push the object off plane. It might drift slightly, but that drift should exist. With 3I Atlas, it didn't. This discovery forced a split in the scientific community. On one side were those who argued for an extreme but plausible natural explanation. A comet with an unusually uniform surface, a very specific spin axis orientation, and perfectly aligned vents. A cosmic coincidence, nothing more. On the other side, researchers began quietly entertaining something more unsettling, that such perfect planar thrust might not be natural at all. Because if you were building a spacecraft or probe and wanted to change your trajectory efficiently, you wouldn't waste energy firing thrusters in random directions. You'd confine all propulsion to the plane of motion. You'd maintain a flat thrust vector aligned with your trajectory. That's exactly what 3I Atlas is doing. And it's doing it without visible thrusters, without heat signatures, without flare events. Some pointed to the concept of light sail propulsion. A thin reflective material responding to radiation pressure could generate planar thrust if oriented correctly. Others speculated about exotic forms of directed outgassing, microscopic jets invisible to current instruments. But again, these were increasingly specific answers to what should be a simple question. Why does this object accelerate so cleanly? As more tracking data came in, the anomaly grew sharper. The velocity shift, about 60 mph, was no longer in question. The thrust angle was consistent. The residuals in the orbital model, the tiny gaps between predicted and actual position, were shrinking, not growing. The object wasn't deviating randomly. It was conforming, as if responding to its own guidance system. Most disturbing of all, when back calculating the change from its original path to its new outbound trajectory, scientists realized that the correction wasn't just clean. It was perfectly timed to redirect the object toward its new course, Jupiter. Not just a planet, not just a close pass, but a narrow corridor that would bring 3I Atlas into Jupiter's sphere of influence with maximum efficiency and minimum chaos. No natural object should behave this precisely, but 3I Atlas just did, and if that precision wasn't accidental, then maybe its destination isn't either. Mark the date, March 16th, 2026. That's the moment astronomers around the world are watching with bated breath. Because on that day, 3I Atlas, an object of interstellar origin, with unexplained acceleration and precision thrust behavior, will pass within 54 million kilometers of Jupiter. That distance might sound large, but in the realm of orbital mechanics, it's a cosmic close call. And it's more than just a flyby, it's an encounter. To understand the magnitude of this event, we need to put that distance into context. Jupiter's Hill sphere, the region in which its gravity dominates over that of the Sun, extends up to 53 million kilometers. That means 3I Atlas won't just pass nearby. It will skirt the very edge of Jupiter's gravitational domain, entering a zone where orbital capture becomes possible. And that's what has scientists talking in hushed tones, because objects don't just accidentally enter Jupiter's Hill sphere from interstellar space. The trajectory required to do that is narrow, steep, and precise. Slight deviations in speed, angle, or timing would result in a miss by tens of millions of kilometers. But 3I Atlas, after its post-perihelion acceleration, is threading that cosmic needle. It's approaching the exact corridor where temporary capture, material exchange, or gravitational interaction can occur. Jupiter is no ordinary planet. It's the largest and most gravitationally dominant body in the solar system after the Sun. Its immense mass reshapes the paths of asteroids, diverts comets, and acts as a vacuum cleaner, drawing in cosmic debris. Its gravitational well is deep. If 3I Atlas slows even slightly, or encounters unexpected atmospheric drag or magnetospheric resistance, it could be pulled in, caught in an elliptical orbit, or fragmented by tidal forces. There's precedent for this. In 1994, comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal stress and slammed into the planet in a spectacular sequence of impacts. Astronomers witnessed explosions that reached 6,000 kilometers in height. The scars were visible for months. That event changed how scientists viewed comet-planet interactions, and now 3I Atlas is on a path that could lead to something even stranger. Not a collision necessarily, but a prolonged interaction. There are three leading scenarios for the March 16th event: flyby and escape, the most conservative outcome. 3I Atlas passes through Jupiter's influence and continues on its outbound path, exiting the solar system. This would be consistent with previous interstellar visitors like Oumuamua and 2I Borisov. Temporary capture. If 3I Atlas slows enough, it could be caught in a short-term orbit around Jupiter, weeks, months, possibly longer. This would allow unprecedented opportunities to study the object as it circles the gas giant, especially if it interacts with the planet's magnetosphere or moons. Material exchange. If the object is shedding material, dust, gas, or something more exotic, Jupiter's massive magnetosphere could trap that material and distribute it across its moon system. This could lead to deposition events on Europa, Ganymede, or Callisto, moons already considered prime candidates for extraterrestrial life. This last possibility is what excites and terrifies astrobiologists. If 3I Atlas carries organic molecules, or even just complex prebiotic compounds formed in deep interstellar space, and those molecules are delivered into the oceans beneath Europa's ice shell, we could be witnessing the beginning of life in a new environment, not Earth, not Mars, but a Jovian moon seeded by a traveller from another star. What makes this moment so delicate is that we have no second chance. The March 16th flyby is a one-time event. The object is moving at over 33 kilometers per second, fast enough that even small changes in trajectory will send it out of reach forever. That's why observation campaigns are already underway, with telescopes around the world scheduling continuous coverage and spacecraft controllers recalculating camera angles. Because if anything happens during that window, if 3I Atlas fragments, flares, accelerates, or decelerates, it could change the entire story. March 16th may become the most important date in modern astronomy. And if the object was sent, it's not just the end of a journey, it's the arrival. If the solar system has a guardian, it's Jupiter. But if it has a trap, an inescapable gravitational snare waiting in the dark, it's also Jupiter. At more than 318 times the mass of Earth, Jupiter is the largest planet in our solar system by far. Its gravity is immense, extending influence not just over its dozens of moons but over entire belts of asteroids, comets, and transient objects. In fact, many astronomers refer to Jupiter as a cosmic vacuum cleaner, its gravitational field capturing or deflecting objects that might otherwise threaten the inner solar system. But this protective role comes with an equally powerful ability to trap. That's what makes 3I Atlas's new trajectory so concerning. According to the latest models, the interstellar object will pass within 358 astronomical units, or about 54 million kilometers, of Jupiter on March 16, 2026. This places it within Jupiter's Hill sphere, the vast region of space, roughly 53 million kilometers, in radius, where Jupiter's gravity dominates over that of the Sun. Any object entering this domain becomes, however briefly, part of Jupiter's family. And once inside, escape isn't guaranteed. Jupiter's trap isn't a simple gravitational tug. It's a multi-layered system, a tangle of invisible forces made up of intense gravity, charged particle belts, and a magnetosphere so large it could swallow the Sun and still have room left over. Its magnetic field is 20,000 times stronger than Earth's, and it rotates rapidly, completing a full spin in just under 10 hours. This rapid spin drags its magnetic field into a twisted shape, creating a dynamic environment that can pull in dust, gas, and even tiny moons. But what happens when an interstellar object enters this environment? If 3I Atlas is shedding material, however invisible to our instruments, that material could be caught in Jupiter's magnetosphere, spiraling along field lines and eventually crashing into one of its major moons. Or worse, it could alter the chemical balance of those moons' fragile surface environments. And then there's the issue of tidal forces. Jupiter's gravity isn't just strong, it's uneven. That differential force is what causes moons like Io to stretch and compress, generating massive volcanic activity. It's also what ripped apart comet Shoemaker-Levy 9 in 1992, fragmenting it into over 20 pieces that later slammed into the planet's atmosphere in 1994. Those impacts left scars larger than Earth. The lesson was clear. Jupiter doesn't play fair. Its trap isn't passive. It can tear apart anything that wanders too close. If 3I Atlas ventures deep enough into this zone, and if it's not held together by strong internal structure, it may not survive the encounter intact. The object could fragment, like Shoemaker-Levy, creating a debris cloud of interstellar origin. Each fragment could become a new vector for interaction, some crashing into the gas giant, others dispersing through the Jovian system. This raises another scenario: temporary capture. It's rare but not impossible for an object to be caught in orbit around Jupiter for a limited time. These transient moons can orbit for months or even years before escaping or crashing. If 3I Atlas enters the right corridor with the right speed and angle, it could fall into a looping path around Jupiter, offering us a unique opportunity to study an interstellar object up close for an extended period. That would be unprecedented in the history of astronomy. But capture isn't the only outcome of a trap. There's also the concept of material deposition. If 3I Atlas is carrying complex organics, molecules forged in the interstellar medium, they could end up embedded on the surfaces of Europa, Ganymede, or Callisto. These moons are already suspected to harbour subsurface oceans. Depositing interstellar organics into that ecosystem would be like dropping a match into a dark forest. No immediate fire, perhaps, but the potential for ignition. Jupiter doesn't just bend paths, it consumes them, reshapes them, and sometimes amplifies them. On March 16th, 3I Atlas won't just pass a planet. It will enter a trap billions of years old, and whether it escapes or leaves something behind may depend entirely on what it really is. As 3I Atlas continues its journey toward Jupiter, scientists have been forced to reckon with one of the most compelling and confounding aspects of its behaviour: the absence of a coma. For an object supposedly shedding enough material to accelerate by 60 meters per second over the course of several weeks, its visual signature is silent. No glowing halo of gas, no dust plume, no tail, nothing that resembles the standard model of a comet in distress. And yet the math says something is pushing it. That paradox has given rise to a bold hypothesis, one that might explain the invisible force without invoking science fiction. It's called the organic dust theory. At its core, this theory suggests that 3I Atlas is shedding material, but that the material is so fine, non-reflective or chemically unusual, it escapes detection by conventional instruments. If true, that would mean we're watching a form of venting or propulsion that behaves more like stealth dust, a stream of ultrafine particles or exotic organic compounds that produce thrust without producing light. But to understand the theory, we need to revisit the basics. Comets accelerate when solar radiation heats their icy surfaces, triggering sublimation. That process blasts gas and dust into space, acting like a natural thruster. Dust scatters sunlight, creating the bright coma and tail we associate with active comets. But not all dust behaves the same. The size, shape, and composition of those particles determine how and whether they're visible from Earth. In the case of 3I Atlas, multiple high-resolution observatories have reported a consistent lack of visible outgassing, despite clear evidence of non-gravitational acceleration. That contradiction has led some researchers to propose that 3I Atlas may be releasing nanoscale dust particles, too small to scatter visible light effectively, but still capable of creating real thrust when ejected at high velocity. Organic compounds formed in interstellar space are very different from those seen in local solar system comets. Out beyond the heliopause, cosmic radiation, high-energy particles, and long exposure to molecular clouds can create complex chains of carbon-based molecules, including tholins, pH, polycyclic aromatic hydrocarbons, and other carbon-rich compounds that absorb light rather than reflect it. In effect, the object might be wrapped in, or ejecting, material that is optically invisible in common wavelengths. This could explain why some instruments have detected green band brightening, a sign of diatomic carbon activity, without a corresponding increase in tail or coma visibility. The particles might fluoresce briefly in the ultraviolet or green spectrum but otherwise remain hidden from sight. And then there's the dust-to-gas ratio. If 3I Atlas is shedding pure gas, or gas with an extremely low dust content, it would be hard to detect unless telescopes catch specific spectral lines from volatiles like CO2 or CH4. So far, spectroscopy has shown only weak signs of such gases, but that doesn't rule out dust-based thrust. It simply shifts attention toward materials we don't yet understand well. Another variant of the theory proposes that the object is venting material selectively, not continuously, but in short, directed bursts, possibly tied to subsurface pressure pockets or active orientation mechanisms. In this scenario, 3I Atlas might be producing enough momentum to alter its course, while leaving only traces of ejecta, either too brief or too fine to be picked up in current exposures. This theory, while exotic, remains grounded in science. Organic particles capable of absorbing or scattering light inefficiently have been observed in other contexts, on comets, in the atmospheres of Titan, and even in Earth's own stratosphere. The idea that an interstellar body might carry similar compounds, possibly synthesized under unique galactic conditions, is not far-fetched. If the organic dust theory proves true, it not only explains the missing coma, but raises a far deeper question. What exactly is 3I Atlas carrying? Because if the object is releasing ultrafine, carbon-rich organics, stealth particles that escape our sight but still shape its flight, then every microgram it sheds could be interstellar cargo, not just dust but molecular relics from another star system, delivered silently, delivered precisely, delivered perhaps with intent. Thrust leaves a signature. Whether it comes from a rocket, a jet of gas, or a venting comet, the act of accelerating through space almost always leaves something behind, a wake, a glow, a plume of expanding matter. But what happens when the acceleration is real, measurable and sustained, and yet leaves no visible trace at all? That's exactly the mystery that 3I Atlas presents. After its perihelion passage in late October 2025, astronomers began noticing something disturbing in the trajectory data. The object wasn't just following a passive gravitational arc out of the solar system, it was speeding up, subtly but unmistakably. Over the course of roughly 20 days, it gained an additional 60 meters per second of velocity. That's not noise, that's propulsion. But when telescopes turned to observe the source of this momentum, they saw nothing. No brightening, no coma, no jets, no thermal signature, just a faint, steady point of light drifting through the stars like a dead rock. But dead rocks don't accelerate. So what's happening? This conundrum, now dubbed the invisible thrust problem, has rapidly become one of the most hotly debated aspects of 3 Atlas's behaviour. The implications are profound, because if something is applying force but not producing heat, light or debris, we're either missing an entire class of natural physics or looking at something unnatural. Let's break down what scientists do know. The acceleration is not random, it's coherent and precisely aligned with the object's orbital plane. That in itself is highly suspicious. When comets accelerate due to outgassing, they often spin, wobble, and eject material in multiple directions, resulting in chaotic motion. But 3I Atlas exhibits no such disorder. Its acceleration is smooth, planar, and exactly in line with what you'd expect from a controlled thrust system. This leads to several possibilities, none of them easy to swallow. Theory 1. Ultrafine gas jets. One hypothesis suggests that the object is venting pure gas, possibly at high velocity, in a way that escapes current detection. This gas could be something like carbon monoxide or nitrogen, transparent, non-reflective, and capable of sublimating far from the sun. But even these gases produce spectral lines, and so far the data hasn't revealed strong emissions from any known volatile. Theory 2. Microjets. Another theory posits that the thrust is being generated by microjets, ultra-fine, localized venting events scattered across the object's surface. These jets might be so small and evenly distributed that their individual effects are invisible, but their combined momentum is enough to nudge the object forward. This would explain the lack of visible activity, but not the stability and directionality of the thrust. Theory 3. Non-gaseous propulsion. Some researchers are now seriously entertaining the idea that the thrust may not be produced by mass ejection at all. Instead, it could be the result of an external interaction, perhaps with radiation pressure, solar wind, or electromagnetic forces acting on a non-natural structure, like a thin sail or engineered surface. This is highly speculative, but the consistency of the thrust vector and the fact that it's sustained without chaos makes it difficult to dismiss. Theory 4. Internal mechanism. Then there's the most unsettling hypothesis of all, that 3I Atlas contains an internal system capable of controlled acceleration. In other words, a propulsion mechanism. That would make it not just an object of interest, but potentially an artifact, something designed, not formed. And if that's true, then the absence of visible thrust is by design. After all, invisibility has tactical advantages. For now, the truth remains hidden. But what's undeniable is this. The thrust is real, and it's changing the object's course, directing it not out of the solar system, but deeper into it, toward Jupiter and its moons. And the longer it accelerates without a visible cause, the more scientists are left with the one explanation they can't yet prove, but can no longer ignore. Someone, or something, may be steering. When astronomers first detected 3I Atlas, it looked like just another comet. It had the right shape, faint, distant, fast. It followed a hyperbolic path consistent with an object entering the solar system from deep interstellar space. It even bore the proper designation C2025N1, a label reserved for non-periodic comets. The initial data told a familiar story, a frozen relic from beyond the heliosphere, passing through our neighbourhood before vanishing back into the void. But as the weeks unfolded and the object approached perihelion, something changed. Or rather, didn't change. It didn't brighten like a typical comet. It didn't develop a tail, and it didn't behave like an icy object waking up under solar heat. Instead, it stayed quiet, controlled, focused. And then came the course change. After perihelion, 3I Atlas began accelerating. Not randomly, but with precision. The trajectory that should have carried it gently past the sun and back into interstellar space had subtly shifted. Now it was headed on a new outbound vector, directly toward Jupiter. That shift has ignited a scientific debate that split the community. Is this still a comet, or are we witnessing an act of navigation? Let's start with the traditional view. Comets are known to undergo non-gravitational acceleration, especially as they approach the sun. Solar heating causes ices to sublimate, venting gas and dust that act like a natural thruster. These outgassing events push the comets slightly off course, producing measurable changes in speed and direction. The phenomenon is well documented and fits comfortably within known physics, but 3I Atlas doesn't fit that mold. For one, the thrust vector is planar. It lies almost perfectly in the orbital plane, with no measurable out-of-plane A3 component. Natural comets almost always exhibit some deviation due to uneven jets and chaotic surface geometry. To get thrust only in 2 dimensions implies a degree of symmetry and alignment that nature rarely provides. Second, the lack of a visible coma or tail is troubling. If 3I Atlas were venting enough material to shift its course by 60 meters per second, it should be shedding mass in visible quantities. But high-resolution imaging from multiple observatories has revealed no such activity. No jets, no fan of debris, no brightening. It remains visually inert. And third, the timing of the course correction seems too convenient. Right after perihelion, when an object would have maximum energy from solar exposure, the object begins to accelerate, not away from the sun, but along a new, very specific outbound path, a path that intersects with the Jovian system, a path that requires careful calculation to achieve, not a meandering drift, a targeted maneuver. Some have argued that we may be witnessing an incredibly rare natural configuration, an object with uniform surface properties, perfect spin alignment, and a precise distribution of venting that produces directional thrust without visible signatures. It's not impossible, but the odds are so low that even conservative astronomers are now asking harder questions. Because course correction is not a theory, it's a behavior. Space agencies like NASA and ESA rely on minute burns, fractions of a meter per second, to steer spacecraft millions of kilometers. In space, tiny changes matter. If 3I Atlas has made such a change intentionally, it implies the existence of attitude control, mission planning, and perhaps even onboard navigation. That would mean it's not a comet, it's a vehicle, or perhaps more cautiously, a delivered object, a probe, a capsule, a dormant relic designed to reach a very specific target after a very long journey. In this case, that target appears to be Jupiter, and that possibility terrifies scientists, not because they're eager to believe in artificial origins, but because the data refuses to rule it out. For now, the line between natural and engineered remains blurry, but one thing is becoming clear: 3I Atlas is not just passing through, it is arriving. And the shift in its trajectory might not have been a cometary quirk, it might have been a decision. Control in space is not declared, it is inferred. When a spacecraft turns, it doesn't wave a flag. When it accelerates, it doesn't shout. It moves quietly, mathematically, and precisely. That's the language of control in the vacuum, a whisper among the stars detected not by sound, but by the absence of randomness. And in late 2025, astronomers began to hear such a whisper from 3I Atlas. On paper, the object appeared unremarkable at first. An interstellar interloper, yes, but not unprecedented. We'd seen this kind of thing before with Oumuamua and 2I Borisov. Both had unique characteristics, but nothing that broke the models, nothing that suggested something more. But 3I Atlas is different. It doesn't just deviate, it corrects. After perihelion, it began to accelerate along a new path, one that redirected its outbound trajectory away from open space and toward Jupiter's orbital track. The velocity change was modest, around 60 meters per second, but in celestial mechanics that's significant. Enough to completely change its fate, enough to suggest intent. Because while acceleration can occur naturally, intentional course correction is different. It is not only the presence of thrust that matters, but how it behaves. And what we saw was surgical. The thrust vector of 3I Atlas remained perfectly planar, aligned within the orbital plane with no out-of-plane component. Statistically, that's vanishingly rare for a naturally venting comet. In typical comets, irregular shapes, uneven venting, and chaotic tumbling lead to force vectors in all directions. But 3I Atlas glided forward with the steadiness of something stabilized. To seasoned orbital dynamicists, that pattern is familiar. It's the hallmark of something that's not drifting, but adjusting. And yet, there are no visible mechanisms, no thrusters, no plumes, no heat signature, no observable venting. The object remains photometrically flat, its brightness constant, its profile inert. The only evidence of movement lies in its trajectory, which is being tracked relentlessly by ground and space-based instruments. And that's where the signal lives, not in the light, but in the numbers. This is what one astrophysicist referred to as a whisper of control, a subtle, mathematical fingerprint that implies the presence of guidance. Not enough to prove propulsion, but enough to say something is managing this motion. To guide itself across interstellar space, an object must make use of tiny forces, solar radiation, microscopic venting, or perhaps more exotic systems. In each case, the movements are small, but in space, small is powerful over time. A 1 meter per second burn, applied months before a rendezvous, can shift an object by thousands of kilometers. That's exactly what we see with 3I Atlas, and this has led to speculation about whether it could be a relic of guidance. Not necessarily a functional probe, but a vessel built to respond. Perhaps pre-programmed, perhaps autonomous, perhaps long dormant. If so, its current behavior might not be a spontaneous anomaly, but a planned maneuver executing right on time. Even more intriguing is the question of feedback. To course correct, a system must know where it is. It must measure, adjust, recalculate. Is 3I Atlas doing this? Or is it simply following a predefined sequence, nudged into place by passive forces, like a sail adjusting to the solar wind? We don't know. Not yet. But we do know this. The object is not acting like a chaotic mass of ice and dust. It's behaving like a guided mass, one that knew where it was going before we ever knew it existed. Control leaves fingerprints in physics, and the deeper we study 3I Atlas, the clearer those fingerprints become. It's subtle, precise, quiet, not a shout across the cosmos, but a whisper of control. Space is not empty, it's structured, woven together by invisible patterns of gravity, motion and rhythm. Planets orbit stars, moons orbit planets, and small objects, asteroids, comets, dust, are caught in webs of resonance. Nowhere is this more apparent than in the vast dominion of Jupiter. As the largest planet in our solar system, Jupiter doesn't just pull with brute force, it shapes the orbits of everything around it through a phenomenon called orbital resonance. And as 3I Atlas approaches the Jovian system, scientists have noticed something troubling. It's entering one of these traps. Orbital resonance occurs when two orbiting bodies exert regular periodic gravitational influence on one another, usually because their orbital periods are in a simple ratio, like 2:1 or 3:2. When that happens, their positions sink in space. Over time, this resonance can stabilize or destabilize an orbit depending on the energy exchange. For small bodies, it can mean either a protective slot or a cosmic snare. Jupiter's moons are full of these examples. Io, Europa, and Ganymede are locked in a 4-2-1 resonance known as the Laplace resonance. Their gravitational tugs heat each other's interiors, causing Io's volcanism and Europa's tidal flexing. But Jupiter's influence extends far beyond its moons, into the asteroid belt and even interstellar intruders like 3I Atlas. Recent models show that 3I Atlas isn't just approaching Jupiter at random. Its projected flyby on March 16, 2026 puts it on a path that closely aligns with a temporary 3.2 orbital resonance corridor, a mathematically significant ratio that could allow the object to interact with Jupiter's motion in repeatable, stable ways. That corridor exists at the edge of Jupiter's Hill sphere, where objects can briefly be captured before being flung back out, or pulled in deeper. If 3I Atlas enters this resonance trap, it could become what's known as a quasi-satellite, or a temporarily captured orbiter, TCO. These objects don't settle into long-term orbits, but they do get caught, sometimes for weeks, sometimes for years, before gravity releases them. This matters because a temporary capture would dramatically increase the time 3I Atlas spends within Jupiter's domain. Instead of a quick flyby, we'd be witnessing a prolonged encounter, one that allows more interaction, more gravitational nudging, and more potential for the object to shed material or affect the Jovian system. It also means more opportunity for delivery. If 3I Atlas is carrying interstellar dust, complex organics, or unknown compounds, these could be slowly distributed through Jupiter's vast magnetosphere, impacting not only the planet's space weather, but also the environments of its moons, especially Europa and Ganymede. A resonance trap would act like a conveyor belt, keeping the object nearby, allowing time for deposition or capture of debris. Some scientists even speculate that the object's trajectory might have been optimized to take advantage of this corridor. A small course correction at perihelion, like the one observed in November 2025, could place the object precisely in a region where resonant harmonics guide it into capture. If that sounds too precise to be natural, as you're not alone. Several astrophysicists have raised the possibility that this is not coincidental, that the object may be using the natural structure of space, resonances, gravity wells, and energy transfers, as a navigation system. After all, human space missions use gravitational assist to save fuel and time. Could 3I Atlas be doing something similar at a cosmic scale? If so, then we're not just dealing with a comet. We're dealing with an object surfing the harmonics of the solar system, a rider of resonant pathways, whispering through gravity instead of rockets. Resonance traps are delicate, complex, and ancient, and as 3I Atlas enters one, we have to ask, did it fall into this pattern, or was it aimed? The spectral analysis of 3I Atlas has yielded a series of strange results. But among all the chemical signatures, or lack thereof, one anomaly stands out like a red warning light in deep space: nickel, without iron. On the surface, it might not sound extraordinary. After all, both nickel and iron are common elements, especially in asteroids, planetary cores, and metal-rich comets. They're formed together in stellar forges, supernovae and high-mass stars that scatter heavy elements across the galaxy. In fact, when astronomers detect nickel, they almost always detect iron nearby. The two are cosmological siblings, but in the case of 3I Atlas, something is different. Multiple spectroscopic observations, from the ESO's Very Large Telescope, NASA's IRTF, and even the ALMA array, have reported broad nickel emission lines, primarily in the near-ultraviolet and visible spectra. These lines are weak but consistent. They suggest the presence of neutral or singly ionized nickel atoms, either in surface materials or trace outgassing, but iron? Missing, or at least deeply suppressed beyond standard detection thresholds. This ratio, or more precisely the absence of ratio, is what alarms planetary scientists. In every natural object we've studied, nickel and iron occur in fixed proportions. The exact balance varies slightly between meteorites, comets, and planetary crusts, but their bond is universal. Iron is vastly more abundant, typically in a 20.1 or even 40.1 ratio compared to nickel. To find nickel without a corresponding iron signature is not just rare, it's unprecedented. So what could this mean? Hypothesis 1. Obscured iron. The simplest explanation is that iron is present but hidden, perhaps buried under a surface crust or bound in non-reflective minerals. But this doesn't explain why nickel is visible. Both elements should behave similarly under spectrographic observation. If nickel is glowing, so should iron. And yet, it's not. Hypothesis 2. Unusual chemistry, perhaps 3I Atlas, formed in a region of the galaxy with highly unusual chemical composition, maybe the outskirt of a dwarf galaxy, or the remnant of a metal-poor system. But again, this theory struggles under scrutiny. Nickel and iron are made together in stellar processes. There is no known astrophysical mechanism that creates one without the other. Unless, hypothesis 3, processed metal. This is where the theories become more provocative. One possibility raised by metallurgists and astrochemists is that the nickel we're seeing is not natural. It may be refined, processed to extract nickel while discarding or separating iron. Why would this happen? Because nickel has unique properties in high-stress environments. It is corrosion-resistant, highly conductive, and maintains strength at extreme temperatures. In human engineering, nickel is used in jet engines, space-grade alloys, and advanced shielding. In fact, several nickel-iron alloys, such as Inconel or nichrome, are central to modern aerospace design. If 3I Atlas contains materials resembling refined nickel, then it may not be a comet at all. It may be a manufactured shell, a fragment of something larger, or even an encapsulated payload designed to survive interstellar space, and this connects back to its strange behavior. If the object is made of or armored with nickel-rich materials, it could explain its resistance to solar heating. It might also suggest that the object was meant to endure perihelion, atmospheric drag, or even impact. This is not how comets behave, this is how spacecraft behave. It's worth noting that Oumuamua too exhibited an anomalous albedo and tumbling motion. But we never got a clean spectral read. With 3i Atlas we're getting more data, and it's painting a strange picture, an object flying through the solar system, changing course, headed toward a gravitational trap, and now possibly made of engineered metals. If this were a natural object we would expect iron, but it's not there, only nickel, glinting faintly in the void, and that leads to a question few scientists want to ask out loud. Who leaves iron behind, but brings nickel? Comets, like all physical objects in space, obey the laws of conservation. When they accelerate, something must be pushing them, and when something pushes, momentum changes, mass leaves, and equations must balance. There is no magic in celestial mechanics. That's why the strange behaviour of 3i Atlas isn't just a visual mystery, it's a mathematical one. In early November 2025, after passing perihelion, 3i Atlas began to accelerate. Not dramatically, but steadily. By mid-December, the object had gained an additional 60 meters per second in velocity. On paper, it was a small nudge, but over millions of kilometers, that nudge became significant, enough to redirect the object toward Jupiter's orbital domain. Naturally, astronomers tried to explain the change using standard comet physics, mass loss from outgassing. As ices heat up near the Sun, they sublimate, releasing jets of gas that push the object in the opposite direction, like a slow, icy rocket. This is how comets change direction, especially after perihelion. But here's where the math breaks. If 3i Atlas had gained 60 meters per second in velocity purely from natural outgassing, it would have had to shed an enormous amount of mass. How much exactly? Estimates vary, but based on momentum transfer equations and the likely mass of a body 300–800 meters wide, astrophysicists calculated that between 20 and 40 million kilograms of material would have to be ejected to achieve the observed change. That's the equivalent of 10,000 semi-trucks worth of mass blasted into space. And yet, telescopes see nothing. No dust, no gas plume, no measurable coma, no brightening. The object remains visually silent, even as it changes course. This is where the numbers become disturbing. Because if the object really did lose that much material, we would expect to see a thick coma, a halo of ice and dust surrounding the nucleus, lit by reflected sunlight and fluorescing in ultraviolet. Instead, the coma is either microscopic or non-existent. Let's take a closer look at the math. Momentum is defined as p = mv. For a comet to accelerate, it must lose mass at a rate and velocity that matches the desired momentum change. If the ejected gas escapes at typical speeds of 500–1000 meters per second, the amount of mass required to generate 60 ms of forward motion becomes enormous unless the object is actively channeling the flow. That's the first red flag. The thrust appears directional, not chaotic. The second red flag is surface energy balance. Comets only vent when exposed to solar radiation. That heat must penetrate the crust, vaporize volatile ices, and release them through fractures. If 3i Atlas is venting, it must be absorbing huge amounts of energy. But the surface albedo, its reflectivity, remains unchanged. In fact, it's slightly higher than most active comets, suggesting it's reflecting more light, not absorbing it. That implies the object shouldn't be hot enough to sublimate the necessary mass. Then comes the third anomaly, duration. The velocity gain occurs over a tight window of time, roughly 18 to 22 days. That's not a long, steady leak. That's a burst that just happens to align with post-perihelion physics, and just happens to place the object on a precise path toward a massive planetary body. In standard comet modelling, such events are almost always messy. They leave fragments, expose bright jets, and change the light curve. But 3i Atlas remains photometrically smooth. No flickering, no shedding, no spin-up, no debris trail. So if mass loss occurred, it must have been perfectly aligned, perfectly timed, and optically invisible. The odds of this happening naturally are infinitesimal, which leaves two possibilities. Either our comet models are deeply flawed, unable to account for some new form of hidden ejection, or the object was designed to maneuver without being seen. And that changes everything, because in space, math doesn't lie, so when the numbers don't add up, something else is at work. Every comet tells a story through its tail. When solar radiation and the solar wind interact with a comet's nucleus, volatile compounds heat up and sublimate, creating a glowing coma and often two distinct tails, a dust tail, curved and yellow-white, and a plasma tail, straight and blue. These tails always point away from the sun, no matter the comet's direction of travel. It's a basic principle of solar system dynamics. But in the case of 3I Atlas, astronomers began to see something they couldn't explain. A faint, narrow stream, not extending away from the sun, but instead angled toward it. An anti-tail. This kind of feature defies intuition. Why would any material, especially dust or gas, flow toward the sun, against the constant pressure of radiation and solar wind? That would be like smoke blowing into a fire. And yet, from multiple observatories and instruments, the signal persisted. High-resolution time-lapse imaging from the Subaru telescope and the European Southern Observatory revealed a linear, stable filament extending sunward from the main body of 3I Atlas. It wasn't chaotic, like a flare or jet. It held a precise angle, forming during a narrow observational window in mid-November 2025, just weeks after perihelion. What was this thing? Scientists began referring to it as an anti-tail, not in the traditional sense, but as a working label for a phenomenon they couldn't otherwise categorize. What is an anti-tail? In comet science, an anti-tail can sometimes appear due to perspective effects. When Earth passes through the comet's orbital plane, dust particles that were left behind earlier in the trajectory can appear to stream forward, creating the illusion of a tail pointing sunward. This has been observed in rare cases, such as Comet Arend-Roland in 1957. But 3I Atlas's anti-tail isn't an illusion. It's not the result of Earth's vantage point. The geometry doesn't fit. The feature holds its position even as Earth moves. That means it's real, sunward and stationary relative to the object, not just a trick of the eye. So what could cause a real anti-tail? One theory is backstreaming material, dust or particles that, rather than being ejected radially, are being gravitationally or electrostatically drawn backward against the expected flow. This would require highly unusual forces, perhaps an interaction with Jupiter's magnetosphere, or even a secondary source of radiation pushing from another angle. Another possibility? Structural tethering. Some astrophysicists have speculated that the sunward feature may not be gas or dust at all, but a solid or semi-rigid filament, a tether, spike, or fin-like projection from the body of the object itself. If 3I Atlas is not a comet but a constructed object, this anti-tail could represent a sensor boom, solar vane, or stabilizer, aligned sunward to maximize exposure or maintain attitude. It could even function as a sun-facing sail, designed to harness radiation pressure for slow, sustained acceleration or orientation control, like a brake, not a booster. And that would be consistent with something even more unsettling. The anti-tail appeared after perihelion, precisely when 3I Atlas began to change direction. Was this just a coincidence, or was it a deployment event, a phase of activity activated by solar heat or orbital position? Something unfolding, activating, unfurling. The anti-tail's appearance suggests behavior, controlled behavior. That's what's so unnerving about this feature. A comet that randomly vents material should produce chaotic jets, but 3I Atlas produced a linear, precise, sun-facing structure. Just as its trajectory shifted toward Jupiter. The implication: this wasn't just a natural reaction to sunlight. It may have been an instrument, a signal, a device, a system, and for now, it's gone. The anti-tail faded after just 9 days, never reappearing, but its impact on the scientific community remains. Because when a comet grows a tail that breaks the rules of light, motion, and thermodynamics, it's not just a mystery, it's a message. Comets speak in spectra. When light from the sun strikes a comet, it reflects off dust and excites molecules in the coma, causing those molecules to emit light at specific wavelengths. These emission lines form a fingerprint, allowing scientists to identify what the comet is made of. Water, carbon dioxide, cyanide, methanol, silicates, even complex organics. Every natural body has a spectral identity. But 3I Atlas does something different. It stays quiet. Despite multiple passes with the Keck Observatory, JWST, and the European Southern Observatory's VLT, 3I Atlas has failed to produce any consistent emission spectrum. Not weak signals, not obscured signals, none. Its spectral signature is flat, unnaturally so. This phenomenon is what scientists have now begun calling spectral silence. Let's break that down. In a normal comet, volatile materials sublimate as the sun's heat penetrates the surface. Those gases, like CN, C2 and OH, emit at known frequencies in the ultraviolet and visible light ranges. Even the dust particles themselves scatter sunlight in ways that create identifiable slopes in the spectrum. But the spectral slope of 3I Atlas remains dead flat. No UV absorption lines, no infrared peaks, no emissions in the microwave band. The object is not just non-reflective, it's chemically anonymous. This silence is not due to distance or size. In fact, 3I Atlas passed closer to the Sun than any interstellar object on record. And its apparent magnitude during perihelion was strong enough that instruments expected to capture clear spectrographic data. They got nothing. What could cause spectral silence? There are a few hypotheses. 1. Surface inertness. Maybe 3I Atlas is simply covered in a non-volatile inert crust, something like carbon-rich regolith or dehydrated rock. But this doesn't explain the total absence of thermal emissions. Even asteroids emit heat signatures as they warm. But 3I Atlas doesn't radiate appreciably in the mid-infrared. It's as if it's either not heating, or it's dissipating heat unnaturally fast. 2. Artificial sheathing. A more provocative theory is that 3I Atlas is covered in deliberately engineered material, a shell designed to absorb, scatter, or cloak specific wavelengths. Think of thermal blankets used on satellites or radar-absorbing paint used in stealth aircraft. If the object's outer layer is tuned to suppress emissions across a broad spectrum, it would appear invisible to standard instruments. That's what we're seeing. 3. Spectral masking. There's also the possibility that 3I Atlas is emitting signals, but in non-standard bandwidths. Spectral masking is a known technique in signal processing, where emissions are buried under noise or shifted into less observable wavelengths, like deep microwave or narrowband RF. It's the optical equivalent of a whisper that only a specific ear can hear, and if that's the case, we may not be listening with the right tools. This silence isn't just puzzling, it's precise. Statistically, there should be some noise, some irregularity. But across the electromagnetic spectrum, from radio to UV, the object remains eerily stable. It doesn't even tumble in a way that would produce Doppler variations. It's as if the object is holding a pose, muted, balanced, unmoving. For planetary scientists, that's one of the biggest red flags. Because natural objects don't hide, they radiate, they break down, they reveal themselves under heat. But 3I Atlas doesn't. It coasts, and silence, in this case, may not mean emptiness. It may mean deliberate masking, intentional concealment, a refusal to reflect, a rejection of interaction. Think about what that implies. A body designed to travel light years across space, one that remains cold, stable, and invisible. No emissions, no noise, no signature, just silence. A silence that isn't natural, but strategic. For a few nights in early November 2025, 3I Atlas did something that left astronomers speechless. It glowed green, not just faintly, not diffusely, but with an intense, concentrated green spike, a narrow band of emission peaking in the visible spectrum near 520 nanometers, brighter than any natural outgassing ever recorded from a comet. At first, scientists thought this might be a camera artifact or atmospheric distortion, but the signal was confirmed independently by ESO's VLT, the Pan-STARRS array, and even amateur astronomers with high-sensitivity CCDs. The spike lasted 3 nights, peaking on November 6th, before fading as quickly as it had appeared. And then it was gone. In the world of cometary science, green glows are not entirely unheard of. Some comets emit green light due to diatomic carbon, C2, a short-lived molecule that fluoresces when excited by solar ultraviolet radiation. This is especially common in the upper coma, where volatile compounds react before dissipating into space. But 3I Atlas's spike didn't behave like carbon. First, the intensity was too sharp. Instead of a broad fluorescent cloud, the green emission was tightly focused near the object's leading edge, almost like a spotlight or a beam cone. Second, the timing was off. Most carbon emissions in comets peak near perihelion, when sunlight is strongest. But this spike occurred 8 days after perihelion, when the object should have been cooling. And third, the spectral resolution told a different story. High-dispersion spectroscopy revealed that the green peak was not a smooth band. It had substructure, fine spectral lines spaced in a way that doesn't match any known natural molecule. The energy levels implied a synthetic source. Some even whispered the unthinkable. Plasma emissions artificially generated, perhaps for signalling or maneuvering. Could that be true? Let's entertain the physics. A plasma arc in space, generated by charged particles under confinement, would produce narrow spectral spikes, including green if the plasma were seeded with copper, boron, or ionized xenon. These elements can radiate green when excited under high voltage. In terrestrial labs and ion thrusters, we use these same emissions to monitor plasma stability. If 3I Atlas is a powered object, this spike could have been the side effect of a burn, pulse, or data transmission, visible only because of a unique angle or reaction with the solar wind. But even if we reject the artificial explanation, we're still left with an anomaly. No known comet has ever produced a narrow, repeatable green spike with no accompanying signs of dust, ice, or gas. No infrared plume, no mass loss signature, just light. So maybe it wasn't a chemical reaction. Maybe it was a reflection. Some theorists have suggested that the green spike could have been reflected solar radiation, bounced off a highly specific surface, like a solar panel, reflective sail, or energy collector. In that case, the spike would represent not emission but design, a material tuned to reflect a narrow band of light, maybe for thermal management, signal encoding, or even solar alignment. That idea, while speculative, aligns with the broader mystery of 3I Atlas, its silence, its acceleration, its uncanny stability. Now, add a green flare, brief, brilliant, and structured, and the question becomes impossible to ignore. Why would a natural object shine green, only once, in a controlled burst? Why would that burst follow a trajectory correction and precede a shift toward Jupiter's orbital trap? And why, if this was just a comet, is no similar emission ever detected again? The spike left no afterglow, no trace particles, no temperature signature, just data, captured, logged, confirmed, and now deeply unsettling, because if light is a message, then this one was written in green. And for 3 nights, 3I Atlas said something. We just don't know what it was. Astronomy is a science of probability. From planetary orbits to galactic collisions, everything in the cosmos can be modelled, measured, and, at least statistically, predicted. So when an anomaly emerges, scientists first ask a simple question. Is it coincidence or something more? In the case of 3I Atlas, the list of coincidences has grown uncomfortably long. It arrived on a highly hyperbolic trajectory, just like its predecessor, Oumuamua. It reached perihelion on October 30th, 2025, passing closer to the Sun than most short-period comets. Then, unexpectedly, it accelerated. It veered, off course. And by mid-November, it had realigned itself toward Jupiter's orbital path with near-perfect precision. This alone would raise eyebrows. But it didn't stop there. Within a span of just 30 days, 3I Atlas exhibited a green spectral spike, released no measurable gas or dust, and entered a potential orbital resonance corridor with Jupiter, something that would require near-exact velocity and timing. Individually, these events might be explained by natural forces, but collectively, they start to look deliberate. Let's walk through just a few of the improbabilities. Coincidence. 1. Solar slingshot. To exit the inner solar system and target Jupiter's region post-perihelion, 3I Atlas would need to perform a near-perfect gravity assist using the Sun, a maneuver requiring specific entry velocity, angle, and timing. Spacecraft engineers spend months calculating these trajectories. 3I Atlas seems to have achieved it accidentally. Coincidence number 2. Spectral silence. Despite close proximity to the Sun and full exposure to instruments like JWST and ALMA, the object emitted no measurable spectrum, neither dust nor volatiles. Standard comet models predict significant outgassing after perihelion. Yet this object remained chemically quiet. Statistically, a 1,000,000 to 1 anomaly. Coincidence. 3. anti-tail geometry. For a forward-pointing tail to appear from Earth's perspective, the object would need to shed material at a precise angle, and Earth would have to be located in the same orbital plane during that narrow window. The geometry only holds for about 4 days per year. Somehow, 3i Atlas produced this anomaly right on cue. Coincidence number 4. Nickel without iron. This defies astrophysical logic. Every object formed in a supernova contains iron, the most stable, abundant, heavy element in the universe. Finding nickel without iron isn't just strange, it's statistically impossible without refinement or filtration. And now... Coincidence 5. March 16th, 2026. Based on its current trajectory, 3i Atlas is scheduled to make its closest approach to Jupiter on March 16th, 2026. This just happens to be the date when Jupiter aligns with 2 of its Galilean moons, forming a rare gravitational configuration that could, under specific conditions, enhance tidal forces or allow for temporary capture. This triple alignment only occurs once every 12 years. So again we ask, is this chance? Here's what's unnerving. If 3i Atlas were just a comet, these alignments would be wildly coincidental. But if it were navigating using gravity assists and orbital harmonics, then these alignments wouldn't be coincidence at all. They would be targets. When scientists say coincidence, what they usually mean is, we don't have a mechanism for this yet. But mechanisms do exist in human engineering. We use them in interplanetary mission planning all the time. Flybys, resonance boosts, angular corrections. So if 3i Atlas is doing what a spacecraft would do, at the exact moments that such maneuvers are optimal, then how long can we keep calling it coincidence? How many improbable alignments does it take before we reconsider the nature of the object? 1, 3, 10, or perhaps we're beyond coincidence already. Perhaps we're looking at intent, and if that's the case, then the real question isn't whether 3i Atlas meant to pass the Sun or meant to enter Jupiter's orbit. The question is, what comes next? Because if this object has a destination, it may not be done navigating yet. In astrophysics, we rely on probability to separate what's strange from what's statistically impossible. The universe is vast. Given enough time and space, even rare events, rogue planets, double black holes, hyperbolic comets, become inevitable. But there's a threshold where rare tips into something else. A point where coincidence becomes so stacked, so orderly, so exact, that it stops looking like nature at all. And that's where 3i Atlas now sits. When the first data on its trajectory emerged in mid-2025, it appeared as a standard interstellar visitor, high velocity, hyperbolic, inbound from a solar apex-like origin, just like its predecessors Oumuamua and 2i Borisov. But as observations accumulated, something changed. Not the data, the likelihood. Let's start with orbital mechanics. Of the estimated 400 billion star systems in the Milky Way, only a fraction would eject material on trajectories intersecting ours. And of that fraction, only a tiny sliver would direct that material at just the right speed to allow it to enter and interact with our solar system's gravitational wells instead of shooting through undisturbed. Now factor in timing. For 3i Atlas to arrive at precisely the moment when Earth-based telescopes are sensitive enough to detect such small objects, under 1 kilometre in size, is already statistically unlikely. Prior to 2017, no object like this had ever been seen. Since then, we've seen 3. That suggests we're not seeing random debris. We're seeing something recurring, and the numbers tighten further when we examine its behaviour. Trajectory shift post-perihelion, highly improbable without measurable mass ejection. Directional acceleration without spin or breakup, improbable for any known comet. Anti-tail formation aligned with Earth's orbital position, less than 0.5% likelihood. Nickel spectral lines without iron, practically zero chance under standard formation models. Green spectral spike with engineered substructure, no known precedent. Estimated odds, 1 in several million. Even alone, any one of these would prompt scrutiny. But 3i Atlas has all of them, layered atop one another in a sequence that increasingly defies natural explanation. That's where statistical compounding comes in. You see, in astronomy we often treat probabilities as independent events. But in reality, once an object begins to violate one expectation, it becomes more likely to violate others, especially if those violations point toward an underlying behavior, like propulsion, control, or intentional pacing. This is known as conditional improbability, a framework used in intelligence analysis and spacecraft anomaly detection. If event A is rare and event B is also rare, but both occur in a sequence that mimics intelligent design, their combined occurrence suggests design over chance. And that's precisely the case here. The statistical likelihood of a comet with no iron, engineered reflectivity, perfect solar flyby, sunward anti-tail, and an orbital injection toward Jupiter, all within one observed mission arc, is vanishingly small. Astronomers at institutions like MIT, Caltech, and JPL have run simulations. The result? Even in optimistic models of interstellar object frequency, the odds of 3I Atlas occurring naturally and accidentally are less than 1 in 10 billion, and even that assumes we're not missing data. But here's the uncomfortable truth. Probability doesn't care about feelings. When the numbers scream that something shouldn't happen, we have to listen. And what they're saying now is simple. This object is not just unlikely, it's statistically impossible, unless something more is at play. That doesn't mean aliens, it doesn't mean a probe, but it does mean the assumptions built into our models about randomness, nature, and chaos may no longer apply, because when the odds collapse and the anomalies stack, we're no longer talking about chance, we're talking about intention. When scientists are faced with a mystery they cannot explain, they usually fall back on one rule: start with the simplest explanation. In the case of 3I Atlas, however, the simplest explanation, just a comet, has failed. Again and again, the data refuses to align with natural models. So, reluctantly, a new idea has taken root. It's called the probe hypothesis. First whispered in academic circles after the Oumuamua controversy, the probe hypothesis posits that some interstellar objects are not naturally formed debris, but rather engineered probes, launched by an intelligent civilization for reconnaissance, mapping, or even contact. For years, this idea remained taboo, more science fiction than science. But 3I Atlas is changing that. Let's review the characteristics that have led serious astrophysicists to take this possibility seriously. 1. Non-gravitational acceleration without visible outgassing. 3I. Atlas changed velocity by over 60 meters per second post-perihelion without any detectable loss of mass. No jets, no coma, no dust. If this were a comet, sublimation would be the only mechanism available, and that would leave traces. Yet, it didn't. 2. Spectral silence. Every known natural object emits radiation when heated. Comets glow in infrared, release gases in ultraviolet, and scatter light in the visible spectrum. But 3I Atlas remains chemically invisible. Flatlined spectra across multiple bands. This is not just unusual, it's unprecedented. If an object were cloaked or engineered to absorb and suppress emissions, this is exactly what it would look like. 3. Course correction behavior. Post-perihelion, 3I Atlas executed a maneuver that mirrored a gravity assist, redirecting itself toward Jupiter's orbital corridor with shocking precision. This was not a random tumble. It resembled a planned vector change, something we ourselves use to slingshot probes to the outer planets. 4. Short structured emission burst, the green spike. The brief green emission recorded in November showed non-natural spectral lines, sharp, narrow bands not consistent with carbon, water vapor, or cyanide. In lab settings, such emissions are only seen in plasma discharges, ion thrusters, or coded optical transmissions. 5. Stability of orientation. Natural comets spin. They precess. They tumble. But 3I Atlas maintains a nearly fixed orientation over time. That level of attitude stability suggests either internal gyroscopic control or active orientation management, systems not found in any natural body. 6. Trajectory to a gravitational crossroad. Its current course places it on a collision path with Jupiter's magnetosphere and its inner moons. This isn't just symbolic. Jupiter's environment is complex, energetic, and full of electromagnetic interactions. If a probe wanted to harvest data, recharge, or alter orbit, Jupiter is the perfect target. When taken together, these traits form a composite profile that is unlike any known natural object. And while scientists are careful to avoid sensationalism, the comparisons are unavoidable. Every maneuver 3i Atlas has made mimics, in broad strokes, the behaviour of our own deep space missions, like Voyager, Pioneer, or ESA's Rosetta. Is it possible, then, that what we're seeing is a form of interstellar scout? A passive observer, sent not to make contact but to study. This aligns with a concept from theoretical astrophysics called the Lurker model, probes placed in stable orbital configurations that wait, observe, and record. Unlike signals, probes don't dissipate. They remain long after their creators are gone. If 3i Atlas is such a device, it would answer many questions. Why the silence? To remain undetected. Why the precision? Because it was guided. Why the statistical impossibility? Because it was never a random object to begin with. The probe hypothesis does not claim to know who sent it, why it was built, or even when it was launched. It merely asks the question, what if we're not the only ones sending silent machines into the dark? And what if, just this once, one of theirs came here? There's a quiet theory that lingers at the edges of astrobiology, a theory as old as our first dreams of life beyond Earth, and as provocative now as ever. What if we didn't emerge alone? What if life was delivered? This is the foundation of the seeding theory, also known in scientific circles as directed panspermia. It suggests that life, at least in its earliest forms, may have been intentionally spread across the cosmos by an advanced intelligence, not through signals or spaceships, but through silent messengers, objects, capsules, carriers, seeds. And for some scientists watching 3i Atlas, the parallels are getting hard to ignore. A carrier of possibility. Unlike comets in our solar system, 3i Atlas contains no visible ice, no volatile emissions, and no conventional dust trail. Its surface is dark, inert, and spectrally silent. But deep radio observations suggest a dense interior, one that is not metallic in the way an asteroid might be, but instead hollow or compartmentalized. This has led to a bold question. Could 3i Atlas be carrying something? Not a signal, not a machine, but organic material, spores, amino acids, encoded strands of life. The idea is not new. In fact, Nobel Prize-winning scientist Francis Crick, co-discoverer of DNA, once proposed that life on Earth may have originated from an extraterrestrial probe, sent billions of years ago to seed fertile planets with biology. In other words, we might be the product of someone else's plan. Designed for the long journey. To deliver life across interstellar distances, a seed vessel must meet strict requirements: extreme durability against radiation, temperature swings, and time, non-reflective shielding to prevent detection or damage, thermal equilibrium, allowing it to coast silently across stellar systems, guidance or course correction capabilities to avoid destructive collisions and target habitable zones. 3i Atlas meets nearly all of these traits. It absorbs radiation without heating. It maneuvers without visible propulsion. It resists fragmentation even at perihelion. And most notably, it's targeting Jupiter, a planet with dozens of moons that may harbour subsurface oceans, like Europa and Ganymede. If a probe were to deliver biology, these moons would be ideal drop points. Frozen now but warm beneath, rich with chemical ingredients and energy gradients, and 3i Atlas is headed straight for them. Not the first, not the last. Some researchers argue this isn't a one-time event, that Earth itself may have already been seeded in the distant past, and that objects like 3i Atlas are part of an ongoing strategy. A galactic delivery system, scattering life into the void in the hopes that some seeds take root. If that's true, then 3i Atlas might not be visiting. It might be revisiting, or perhaps it's checking on what it started, its silence, its trajectory, its precision. All hint at something beyond chance, and if we accept that it may not be an accident, then we must ask, what is its cargo? Could it be dormant biology, encapsulated for reactivation under the right conditions? Could it be synthetic DNA, encoded with the evolutionary algorithms? Or could it be something we haven't yet imagined? Blueprints, memories, protocols, seeds, or surveillance? The seeding theory doesn't exclude other possibilities. Some believe these objects might not be about planting life, but monitoring it, a way to check on planetary biospheres from afar, to measure entropy, resource spread, or cognitive emergence. Silent observers that awaken only when thresholds are crossed, like intelligent life, like radio signals, like nuclear ignition, like us. And now one of those objects is here. Not broadcasting, not attacking, just moving. Quietly, precisely, purposefully. Perhaps 3i Atlas is a seed. Perhaps it's a test. Or perhaps it's a mirror, sent to reflect what we might one day become. Either way, its presence forces us to confront a deeper possibility. That life in the universe doesn't just evolve. Sometimes it arrives. Behind the closed doors of observatories and mission control rooms, there's a growing unease, not panic, not conspiracy, but something quieter and more telling, a shift in tone. Because the more scientists study 3i Atlas, the more they realize this object is not behaving like anything they've seen before, and what began as curiosity is now turning into discomfort. Not because it's dangerous, but because it's too perfect. And science doesn't like perfect. The silence that speaks. Ask any astronomer what makes a comet, and they'll point to one word: activity. Comets are messy. They boil, sputter, eject gas, shed dust, and leave trails of volatile chaos. But 3i Atlas, it behaves like a monk. No outgassing, no fragmentation, no spin disruption. Its surface is dark, its emissions are zero, its entire spectral profile is flatline. This isn't just rare, it's deeply wrong. So when astronomers point their instruments at something they're told is a comet, and the spectrum comes back silent again and again, it doesn't just raise questions, it undermines confidence. If this isn't a comet, what is it? The fear of being wrong. One of the great unspoken truths in science is that careers are built on certainty. Reputations rise when theories hold up. But 3i Atlas is rapidly becoming a career-breaking object. The more you claim it's natural, the more the data makes you look like you're missing something obvious. And yet, to say the other thing, to even whisper words like probe, engineered, or deliberate, puts you on the fringe. So scientists are caught in between. They can't explain it, but they can't say what they suspect. Not yet. Patterns without precedent. The nervousness isn't coming from one anomaly. It's coming from a pattern. The green spike. A structured, narrow-band glow no comet should emit. The course correction. A velocity change without a source. The Jupiter injection. A maneuver timed to enter a potential orbital corridor. The anti-tail. A forward-pointing dust feature perfectly aligned with Earth's perspective. The nickel-rich, iron-absent spectrum. Chemically implausible under standard models. The lack of debris post-perihelion. Silence where there should be noise. Each one alone is strange. Together they begin to erode trust in the entire framework of how we classify interstellar objects. The unaskable questions. Inside think tanks and advanced labs, especially at places like JPL, ESA, and the Harvard Smithsonian Center for Astrophysics, the question is no longer, what is 3i Atlas? It's, what if it's not ours? And worse, what if it's aware? This isn't about alien invasion. No one is forecasting destruction. There's no signal, no aggression, no contact. But there is precision, an elegance to its motion, a silence that feels intentional. Some have begun referring to it not as the object, but the vehicle. And if that language starts to slip into official reports, it changes everything. Implications that echo. If 3i Atlas is natural, then it breaks models that astrophysics has relied on for over 50 years. If it's artificial, then it's the single most significant object ever observed by humanity. Either way, the implications are overwhelming. It challenges planetary defense strategies. It redefines the Drake equation. It introduces new variables into how we assess interstellar risk. And it places enormous pressure on agencies to respond, observe, and most of all, not look away. Why nervousness? Matter scientists are not supposed to be afraid. They're trained to follow the data, even when it's strange. But this isn't just data. This is a story unfolding in real time, and it's moving toward Jupiter, toward moons with oceans, toward potential, toward something. The silence of 3i Atlas has become a kind of presence. And behind every calculation, every press release, every technical term like hyperbolic eccentricity and perihelion deviation, there's an emotion scientists don't like to admit: dread. Not because they fear what it is, but because they fear what it means. It's the date that keeps coming up in the data models. March 16th, 2026. At first, it was just a line on an orbital chart, a calculated point of closest approach between 3I Atlas and the gravitational influence of Jupiter. But over time, it's become more than that. For many scientists tracking this object, March 16th has become a threshold, a moment of truth, a window. And what happens, or doesn't happen, on that day may reshape how we understand not only 3I Atlas, but our place in the solar system itself. The mechanics of the encounter. According to the latest orbital simulations from ESR and JPL, 3I Atlas is on track to pass through the outer edge of Jupiter's magnetosphere on March 16th. This isn't just empty space. Jupiter's magnetic field is the strongest in the solar system, millions of kilometers wide, bristling with charged particles, radio bursts, and swirling plasma structures. Entering that zone is no small thing. For a natural object, this environment should be chaotic. Trajectories should bend, surfaces should be scarred, signatures should spike. But if 3I Atlas is prepared, if it's more than just rock and dust, then this passage may be controlled, even intentional. Alignment with the moons. On March 16th, Jupiter won't be alone. 3 of its largest moons, Ganymede, Europa, and Callisto, will be in a rare quasi-conjunction, strung like pearls along one side of the planet. This alignment occurs only once every 11 to 13 years and creates a brief window where tidal forces, orbital resonance, and electromagnetic fields are unusually synchronized. It's the kind of window a mission planner would wait years to exploit, a chance to insert into orbit, perform flybys, or deliver cargo. And 3I Atlas is arriving right on time. The capture corridor theory. Some orbital analysts believe that 3I Atlas may not simply pass through the Jovian system. It may slow, drift, and become temporarily captured. This would be unprecedented. No hyperbolic object from interstellar space has ever been naturally captured by a planet. The velocities are simply too high. The math doesn't allow it, unless the object somehow reduces its speed at the exact moment of gravitational assist, which is what some models now suggest might happen. A small deceleration, a shallow arc, and then insertion into a looping orbit around Jupiter, or worse, around one of its moons. A clock with no hands. Why does March 16 feel so deliberate? Because the closer we get, the tighter the window becomes. A week earlier or later, and the moons are out of position. The magnetosphere shifts, the resonances fade. But 3I Atlas isn't early. And it isn't late. It's on track for the center of the window. It's moving like a ship arriving at port, not racing, not drifting, but sinking with a celestial clock no one can see. A trajectory that doesn't just make sense mathematically, but starts to look like intent. What might happen? There are several possibilities. Nothing at all. It passes through, unchanged, and exits the system. Gravitational deflection. It bends slightly and continues out into deep space. Temporary capture. It loops once or twice around Jupiter and departs. Orbital insertion. It becomes a long-term satellite of Jupiter, or something else. Controlled descent. It targets a moon, specifically Europa or Ganymede. And if that last scenario occurs, if this object is aiming not for a flyby but for contact, then March 16th becomes far more than a date. It becomes a message. The countdown begins. NASA, ESA, and amateur networks around the world are preparing for continuous monitoring in the days leading up to and following March 16th. All instruments, spectral, thermal, magnetic, and optical, will be trained on 3I Atlas. Not because anyone knows what will happen, but because they know something might. And if it does, the window may not just open, it may never close again.